So today we are going to speak about two things. The one is the continuation of implicit neural representation that we saw last class. And the second is a very nice and interesting topic called neural rendering. Okay. So let's move on. Just a small recap from last time. So last time we discussed deep image spiral. By the way, that's the light of this light disturb you? It's okay. Are you okay with it? Okay. Do you know how to switch it off? Okay. If somebody knows we can switch it off, it will be okay. Okay. So we spoke about deep image spiral in the context of English problem. The network see only the degraded image for that task. We have the CNN. The input to the network is some noise, which is mapped to the restored image. And this is the loss that we are going to minimize, such that the restored image, the downsampling of the restored image is going to be similar to the degraded image. And we understood that the network, after training, the network weights parameterize the restored image. That's what we had last time. Okay, and what we discussed also last time is the classical rendering. When you have the scene definition, which is the camera which takes the pictures, and the geometry, which means the shapes, the position of the shapes, etc., etc., the materials which the shapes are consisted of, and the setting of the lights in the scene. And you take it and you blend it somehow, get some photorealistic image. However, we understood very well that it's very challenging to solve the rendering equation. We understood also why. Since the rendering equation should take into account not just the direct light, but also the indirect light, which means that we take the light that comes from the source of light, and we fall on the surface, we reflect the surface, and then reflect it from the surface. And you should know all the light field in order to know how to describe the rendering image. And we understood also that the rendering equation is recursive due to this indirect light. Okay? So if problems are difficult, what we are going to do? To use deep learning. Okay. If it disturbs, I can call somebody that will. You want me to call somebody to put off the light, or are you okay with this?
It's indirect.
Maybe it's from here. I think it's from here somehow. It's okay. Leave it like this. It's okay. Thank you. Okay. So just what is we are going to cover two subjects today, two topics: neural rendering, which is deep-based computer graphics, taking all the ideas from classical rendering and put them together in a way that you can control the illumination, the camera parameters, the pose, the geometry, the appearance, everything. We are going to blend it in a neural way and get a photorealistic image or photorealistic images. In order to do neural rendering, we need to know how to represent scenes by implicit representation using the network. It's going to be related to what we have solved so far with the deep image spiral. We're going to understand how to parameterize geometry, 3D volumes, continuum function, all of this in our network. Okay? But before this, I would like to let you have some motivation. And I would like to ask the question, why not utilize geometry of scene by an explicit representation? Do you remember what is explicit representation of geometry? We just talked about it last time. For example, triangular mesh, it's explicit representation, okay? So why it's less beneficial to employ explicit representation in neural nets? Okay? It's possible, but it was done, but it's less beneficial. So what is explicit representation actually of the scene? So remember that we have some scene, and actually we are interested in the boundaries or the surface of the object. That's what we are interested in order to do rendering. Okay. So what is explicit representation? Actually is the discretization of the object geometry. And there are a few ways to model it. The one that we spoke last time, triangular mesh. You take the surface and you cover it with the triangulars that are connected like this. Another option is using voxels, 3D pixels like this. And another option is using point cloud. Okay, so this is the most common options to use to employ explicit representation of a scene or a shape or an object. Okay. Let's see the drawbacks and the advantages of using explicit representation and how does it affect the neural nets. Okay, so we discussed last time a lot this kind of representation, the triangular mesh, and let's try to understand how we are going to use it, when we are going to use it, and how does it affect our performance. So let's take a very, very simple example. You have a target geometry like this, and the idea is to use some triangular mesh. In this case, it's not triangular mesh, it's lines instead of triangular because we are in R2 and not in R3. Okay, so we take the line segments like this, and we have to start from something in order to move to the target geometry. And we start from some circle with some nodes and line segments, and you want to do gradient-based optimization in order to move from this initial geometry to this geometry. Is the problem clear? Okay, so let's start. What does it mean in order to do it by optimization? So what do? We have the initial geometry. We compute the gradients. We fix the geometry according to the gradients. We update the position. We do it once again. Okay, once again, and now it's okay. Okay, now it's good. It exactly represents the target geometry. However, it seems easy, but life is not easy. In general, in the scene, we have many objects, not just one. So you have to ask the question how to move from this initial geometry to, we have to split the initial geometry in order to get some splitted object. It's possible, but it's not an easy task. Okay. Also, you would like to move from some initial geometry to some other topology. The topology of the donut is different from the topology of the circle. Another complication. So it's not easy to optimize the mesh triangulation in order to move to some target geometry. Okay. And also here you have some complication because the bit here, for example, is very delicate. You would like to get the fine details, but you would like to stay with the smooth details. Okay, just to explain that it's not easy to optimize using the mesh. So let's try to understand what happened with the voxel representation, other representation. Okay, so here the optimization is quite straightforward. This is easier. This is the target geometry. This is the set of pixels that I'm going to would like to represent this target geometry by a set of pixels. I'm doing similar things, start with something, and then I'm doing some gradient descent optimization. I have some loss, and I do some iterations, and eventually I get to this representation. And here, the target geometry, if it's fitted to object, is very easy to optimize. It's not difficult like with the mesh. However, it depends on the resolution of the voxel or the resolution of the pixels. For example, this reconstruction is not very good for this target geometry because the resolution is quite poor. And this is the main drawback of using voxels in order to represent 3D object. Okay. So I would like to conclude. We have trade-off. We can use the mesh representation, which has small memory footprint, but hard to optimize. Or we can use the voxel representation, which is easy to optimize, but can have large memory footprint. Okay, that's the idea. Therefore, there are some other ways to represent the geometry. For example, using implicit continuous representation. So let's dive into it and understand how does it relate to neural networks. Okay. So what is implicit representation? For example, we have this sphere. We can represent it by x squared plus y squared for this way equal to 1. And we have this donut. We also can represent it by some closed form function. But in general, we have some object which is very general. To invent algebraic expression and to tailor them to to fit this general shapes is going to be very difficult. So the idea is to do something else. And what is the something else? Use more expressive implicit representation. What do I mean by that? To look for function or side distance function such that the zero level set of the function in R3 is zero over the shape. You understand what do I mean by that? So you have a function which is defined in R3, and the zero level set of the function, which means that where the function is going to be zero, describe the surface of the shape. Okay, that's the idea.
So that's exactly the same problem as the one that you just said is hard.
For example, here, yes, see it. Just let me.
It's just moving all the variables to one side and putting the C on the
Yeah,
other.
yeah. It's exactly this. For example, in the case of the sphere, f1, fx, y, z, for example, in this case, is going to be x squared plus y squared plus z squared minus 1. And the zero level set of this is exactly the sphere. You are right. But now we're going to see how to invent a implicit representation without looking for such type function. Okay, that's the idea.
So with try to real images or in pictures, like it's a separate function for every object. There's like in the pictures, all of them are surfaces.
Okay. Let's see how does it work. Okay.
Surfaces. Like,
Okay. Let's see how. Yes. So in many cases, it's boiled down to deal with objects, masked object. In other cases, can be something else. But okay, let's see how does it work. Okay. Okay. So how to represent a general shape with implicit functions? So let's take this L shape. It's called just a general shape. We do not have by mind just an expression like this, okay? And let's try to understand how we are going to represent it, okay? So we'd like a function, but outside is going to be positive, inside is going to be negative, and on the surface itself, on the shape itself, is going to be zero. This is the idea. Okay? So the surface is going to be represented, this is in R2, but I'm speaking about R3, it's going to represent it as the points such that the level set of S is going to be, of F is going to be zero. Let's call this set of points, okay? Okay. There are at least two ways to do it and more. The first one is called occupancy, which will indicate a function, which means that inside I'm going to have some a negative value and outside positive value. And on the shape, I'm going to have zero. Okay. Another way, which is more general, is called side distance function, which means that inside, for every point, I'm going to have the negative distance to the surface, and outside, I'm going to have the positive distance to the surface, and on the surface itself, it's going to be zero. Are you familiar with side distance function? Okay, so this is the idea of side distance function. This is why does it called like this? Because every point characterizes the distance from the point to the surface. And the distance is signs. Inside is going to be negative and outside is going to be positive. Okay, and on the shape itself is going to be zero. Actually, this sine distant function has a theoretical closed form PDE that solve it, and this is the PDE. Okay, this is called iconal equation. You are familiar with this. And if you solve this iconal equation, you are going to get sine distant function. What does the iconal equation mean? It's PDE, it's non-linear PDE, partial differential equation, which says the following: on the surface itself, I would like to have on the boundary 0, and in the interior, I would like to have a function such that the magnitude of the gradient, okay, of the function is going to be 0. This would yield to sine distant function. Okay, we're not going to solve it. We just want to give you some intuition. Okay, so this is the way the sine distant function can be calculated. So before we are moving to neural nets, I would like to recap the properties of the implicit representation. Implicit representation allows to have continuous representation in contrast to explicit representation, which discretize the object. Can represent arbitrary topology, arbitrary resolution. It's not limited by the memory footprint. It has some geometric quantities like normals. And what is very relevant to our talk today, it can blend well with deep learning techniques. And let's try to understand how it's going to be blend well with deep learning techniques.
So implicit representation, you are calling anything that is level surfaces on three-dimensional functions? Exactly.
But it's going to also now, we'll see, we're going to discuss how it's going to be represented by neural net. So 5 years ago, more or less, concurrent works paid attention to the idea of implicit neural representation. The work are in some way similar, but in some way different, the way they do the training phase. Okay. The idea is the following. Just let me give you the intuition and then dive into the details. So the idea is the following. You give me at the inference stage, okay, in test stage, you give me a point in R3, X, Y, Z. It forward, flow here in the MLP, like what you see here. And finally, you get one value, for example, which can be the indicator function or the sine distant function. This is the idea. This is the idea of the implicit representation in neural nets. How is it trained to be very useful like this? We'll see in a minute. But the idea is the following. Give me a position in 3D, and I'll give you some function, which can be color, which can be indicator function, it can be sine distant function, and this is the idea. Let's see now how we are going to train the network in order to be able to get this implicit representation by the neural network. And this is the core. Yes. Yes.
The target of this network is to calculate the distance map.
For example, yes. And you do it by, you take some samples, for example, just to have some, you take some samples from the 3D by some way, and you learn propagate it through the network in such a way that after doing some training, okay, the obtained weights in the neural network represent the shape in implicit way. And then you take a new sample that you didn't see, and you'll get something which is related to the volume that you just studied. Okay? Yes.
It seems like more classical machine learning way, right? Like SVD or.
It's related. Yes. Let's see. Somehow it's related to it. Yes. But in general, this is the idea of many complicated works. But the core of the complicated work is this simple MLPs, some layers of MLP, and such that the input is the position and the output is some function, in our case, an indicator function or sine distant function. Okay, and you optimize for the theta of the network, all these weights, such that you'll have this characterization. In one of the works, the work by the group of Yaron, by Matan Atzmon et al., they showed very simple, they showed the theorem which is related to universality, which says the following: any watertight piecewise linear surface can be exactly represented as the null level set S of MLP with value activation. This is a nice theoretical result. However, it's limited to piecewise linear surface. Okay, but it's nice that they showed. Okay, so let's move on. Okay, so how to learn implicit neural representation? Okay, we would like to have such representation using the network such that if the network predicts 0, we know that this point is on the surface. If it predicts something else, this point is not on the surface. Is this clear? Okay. So how to learn implicit neural representation? Mainly there are two ways: supervised and unsupervised. Full 3D supervision and some unsupervision or semi-supervision using the raw data. So let's try to understand what do I mean by full 3D supervision. So there is a seminar work called occupancy networks that somehow take the 3D geometry in a supervision manner, we'll see in a minute how, and classify between points that outside of the object and inside the object. In a minute, we'll see how. And after training, the neural net represents the surface. Okay.
What is it that we're trying to exactly, like what do we have to start with and what are we trying to do?
In a minute, you will understand. Then you get some continuous implicit representation of the surface, and then inference you use queries of 3D points, and you are able to construct the 3D surface. Let's see what do I mean by that. Okay. Okay. So, for example, here, this is the surface. This a linear surface, and the neural net try to classify between points on the left side and the right side. And then for some threshold, the output of the neural net, which is going to be a number between 0 and 1, for the threshold, which is equal to tau, we're going to get points on this linear surface. Okay? So you know that you need to classify between the red points and the blue points.
But we have a point cloud, we have a capture.
Okay. In this case, they have a point cloud. And since it's supervised, they worked hard to differentiate between points which are outside of the bench, for example, here, and points that are on the bench, for example, here. Okay, they had to do some very expensive pre-processing, and this is the drawback of supervision. They did very expensive pre-processing, okay, such that they could classify between points here and points here. Okay, okay. So actually, for example, these points are going to get occupancy 0, and this point are going to get occupancy 1. Okay.
What's this tau against, like a small value?
For example, 0.5. Yes, you have values between 0 and 1, and the tau, which is, for example, 0.5, is exactly the surface that we are going to. It's the level set of the surface that we are going to represent. Okay. Is this clear? Okay.
I have a question.
Yeah.
Is the 3D shape, is it computer generated, or is it something that they scan from a physical layer, from the physical world?
Computed. What do you mean by that? By LIDAR or something? What do you mean by that?
They just generate like a 3D bench from a CAD software? Or
I'm not sure exactly, but it's a very common data set that they use. Data set of point clouds, and that's what they use. I'm not sure how it exactly was taken.
Okay.
It's following this question about computer net. It's like you said that they did a very hard job to distinguish for this picture, but what's the point of doing this all hard job if you can just start from what you already know? The
Because,
exact equation?
okay, several things. They can generalize and learning for a class and not just for, and then they can generalize. For example, you take a bunch of chairs, I don't know, a bunch of tables, and then you can generalize to other tables with distancing. You can make shape completion, for example, if you, some other tasks. So, okay, so they use it for other tasks. But indeed, they work very hard in order to get this supervision. This is, for example, a result by their work. I'll just make it very fast, but when you have, when you send queries to the neural net and you understand that this is the inside and this is the outside, you can do something which is called marching cubes, and you can get the surface itself in good resolution like this, and that's what they did. And they get, after having these queries, they can use this marching cube algorithm and get triangular mesh, and then they can project it rendering. Okay. Okay, this is some result from the work. Is this clear? Is this the idea of the occupancy map is clear? So just to recap, the occupancy network learning nonlinear function between the position at R3 and a number between 0 and 1. The input is the position, the output is the probability of the occupancy, and the decision boundary, which is for tau equals 2.0, represent the surface of the reconstructed shape. Okay, this is related to your other question.
What's the loss in this case? The difference between the distance function and the actual?
Yeah, exactly. Not distance function. In this case, occupancy, it's not distance. Okay. L2 loss, yes. So after training, the weights of the neural network represent the surface. We have full 3D supervision. And this is actually the caveat, because the full 3D supervision is complicated and expensive. Okay. There's also a work called Deep SDF that made similar thing with SDF, essentially from almost the same year, I think. So can we do it without very full supervision? And the answer is yes. So let's say we have point clouds and we have the point in the point cloud. We would like to approximately compute the sign distance function in order to get the surface defined by this point cloud. And we would like to do it without any additional preparation of data or supervision. It turned out that it's possible to do it. So remember the Iconal equation. This is the Iconal equation that just discussed, remember? Okay. So when the Iconal equation works very well, when the surface is smooth and you have uniqueness and existence, etc., etc. But what happens if I'm doing the following stupid thing? I'm going to take to move from this smooth surface and to take point, just sample of point, and try to solve the Iconal equation. What would happen, do you think? I'll get one solution, more solution. I can get many solutions. I'm going to get the desired solution and also some crazy solution which is not smooth. If I'm solving the Iconal equation, literally like solving 3D. However, remember that neural nets are sometimes lazy and they boil down to the simple solution. And if I'm going to use neural net and use this loss, I'm going to, this solution is going to disappear and I'm going to stay only with this solution. Okay, I will not get the crazy solution. So it means that I can sample points from the cloud of points and use this loss. What is this loss? This loss says that on the surface, I would like the points to vanish. In the other point that I sample, I want to solve the Iconal equation with some factor here lambda. And due to the inductive bias, like what we had last time when we spoke about the inductive bias of the neural net, we get some regularization using the neural net, nothing else. We are not going to introduce any regularization by using the neural net. We get the smooth solution and not the crazy solution. And this is also true for other cases like this. Okay, I'll always get the smooth solution, not always, but most of the time I'll get the smooth solution and not some crazy solution. So I can sample point without any supervision. Okay, I can sample points from the point cloud without any additional supervision and can solve the diagonal equation. I can solve the side distance function and get result. This is work from the group of Yaron by Amos group et al. And for example, here I have some cloud of point of a car, and these are the surface of the car, and these are the outside level set, and this is the inside level set. Solved it very nicely. It's called IGR, implicit geometric regularization. Any questions?
I think in the point cloud, you have all the points on the boundary.
On the boundary, yes, the point only on the boundary. This is the idea of surface. Always the points are on the boundary. That's it. Yes. Okay, and also they proved something about the inductive bias, also a limited theory, but for the linear case, the Gaussian descent of the linear model with random initialization converges with probability 1 to a reproducing plane. Also, although it's limited, it's nice to understand that the network has some inductive bias, like what we saw last time. Okay, let's move on. Again, without any supervision, we spoke about point cloud, we spoke about 3D supervision, but now we'd like to speak about just images. I have just 2D images, a collection of 2D images. And now we're going to the stage of neural rendering, okay? What do I mean by that? I told you that in neural rendering, you have a 3D surface, and you have the scene definition, and you shoot arrays, and you render, etc., etc. And here I'm saying something else. That's the 2D images, that's it. And actually, I want to use these 2D images, and also I have the camera position like this, camera position orientation. I know each image is occupied with the camera which takes this image. And now I tell you that I'm going to use these images and to do a few things. Actually, to reconstruct the 3D volume, and then to be able to render new views. So I'm going to use these 2D images to have the surface that we're looking for, and then to render new views. That's the idea of neural rendering. Okay, and this is going to be done in implicit representation. We'll see in a minute how. But is the idea of neural rendering clear? Okay. So the idea is to start with 2D images, to have some approximation to the geometry and to the appearance, and then to be able to render new views. Okay? So also here we are going to rely on a implicit neural representation. I'm going to have the position, and then I'll get some function that related to the surface, okay? To the scene, to the surface. Okay? So, today we are going to discuss a very special class of neural rendering. It's called neural volumetric rendering. Next class, you will understand what is neural surface rendering. Lior Yariv is going to speak on neural surface rendering. So let's try to understand everything that is going in. So this is work was done in Google. It's called NeRF. Somebody heard the buzzword NeRF. We're going to speak about NeRF. And let's do it step by step, because there are some issues that are very delicate. I would like to try to understand it, to explain it very well. So what is rendering? In the neural context, actually, it's like in the classical context. You would like to compute color along ray through the 3D space. You would like to say, this is my camera, I shoot a ray. From this pixel, I shoot a ray to the scene. I would like to know what is the color of this pixel. It's exactly like the classical rendering. However, I want to do it using neural net. So I want to represent my scene using MLP, like what we saw before, and not using a voxel grid or triangular mesh, the input is going to be the location and the output is going to be the scene properties. By the way, the scene properties can be the sign distance function, the indicator function, the color, the density, the BRDF, many things. However, in contrast to what we discussed last time, when we say that I have a surface like this, and this is my camera, and I shoot a ray, I would like to understand when the ray intersect the surface, intersect here, 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 and here. Here they take another direction, and this is the claim for fame. They use volumetric rendering. In this way, they do not have to deal with concrete ray surface intersection, and this makes things easier. And also, they give them some advantages. Let's see what exactly why, and what is volumetric rendering, okay? So, actually, as I said before, we have a camera, we shoot a ray from a certain pixel, and this is the scene representation, which is characterized by some NLP, and we want to know how ray interacts with the scene. So, when we deal with surface rendering, would like to know, like what I just showed here, would like to know how this ray, or where this ray intersect the surface, like what you see here, okay? And you have to look, and we discussed this last time, which you have to check for the hits of the ray, and you have to understand it's expensive, budget. However, what they suggest, they suggest the following. We do not deal with intersection of rays and surface. We are going to implicitly represent the entire volume. And since we are going to represent the entire volume using the MLP, we are going to shoot a ray and to sample points on the ray, like what you see here, and to understand what happens at this point, and then to integrate this information. This is called volume rendering. How they're going to do this? In a minute, we'll see. Okay, but this is...
I'm sorry.
Yes.
When you say points on the ray,
Mhm.
you mean the points in space or the points on the distance of the ray, regardless of how the ray is?
The points you shoot a ray, this is the 3D, points on the ray. Points on the ray that eventually the neural net is going to represent the scene, the 3D scene, and it's going to be possible to collect the information from this all point and to do something which integrates the information. Okay, so we are going to speak about NeRF, which is representing scene as neural radiance field for view synthesis. This is the paper, this is a seminal paper. Made a lot of buzz 3 or 4 years ago. After NeRF, there are work which is called MIP-NeRF, PEG-NeRF, etc., etc. I don't know, maybe hundreds or even more works just came after this work, this idea, and they made a lot of impact. And I think it's very nice work. So in NeRF, the idea is the following. I'm going to go from high level to low level, so bear with me, please. So the idea is the following. Every time we speak about NeRF, we speak about a certain scene, just one scene. Every time we want to use NeRF, we train for one scene. Want to use it for another scene, you need to do the training once again. Every time you have a collection of images, you have to train NeRF once again. It takes, by the way, a lot of time. And only after you train the scene, you can use it for the certain scene, okay? So I'll take the input images. Each of the images is occupied with the position of the camera. I optimize the NeRF, the neural net, in a minute to understand how to optimize, in a way such that it stores in the neural net the representation of the scene in the weights of the NLP. And then at inference, I can render new views. I can take, for example, this position and render a new image. I can take this position and get new images. Okay? This is the idea. Is the idea clear? Let's now dive in. Okay? So what happens at inference? Okay? In general, when I'm speaking about neural nets, I prefer to explain first what happened in inference, and then to explain what happens at training. So let's try, because the inference, let me, in the inference, I can understand what is the input and what is the output. Okay. So let's say that I'm after the training, the scene is represented by MLP. Okay. The input to the neural net is 5 parameters: the location, X, Y, Z, and the viewing direction, which is represented by theta and p. Okay. What is the output? Output is the volume density, in a minute I'll explain exactly what, which is related to the opacity, and the radiance emitted a direction, this direction, at this point. I'm going to do some protocol that you will be more with me. Okay. So if this is the camera and this is the image plane, I'm going to shoot a ray. Okay. Okay. This ray has some direction in 3D, which is denoted by theta and phi. Okay. After I'm shooting a ray. Okay. Just a minute. I'm shooting a ray. I'm going to sample point on the ray. Okay. This is XYZ, another XYZ. Okay. And the input to the neural net is a position plus the direction. And the output is going to be the density. What do I mean by density? If there is no object, the density is going to be 0. If there is some object, the density is going to be some positive number. Okay? Density actually is related to the opacity of the object. If it's opaque, it's going to be large number. If it's nothing, it's just air, it's going to be 0. Okay? And also I'm going to get the radiance, the light transmitted in this direction of X, Y, Z and theta phi. Okay? Radiance, like what we had last time, it's the emitted light in some direction. In this case, in direction of the viewing direction. This is the viewing direction. Just let me know if I'm clear.
The radiance, how do you read it?
Right?
The radiance, how do you read that?
The radiance?
Yeah, but the other thing is just to sampling the point gamma inside a surface.
The radiance is also always a function of the point and the direction. This is exactly what we have here. The point and direction. Okay? Just let me know if this is clear or I need to explain again. Is the density is clear? Okay. Okay. So let me see. Oh, this is the input, this is the output. And then we'll see how I'm going to have a new position, which is not in the training set like this, and I want to render a new image like this. We'll see now how we're going to do it. Okay. So the idea is the following, like what I just draw here, made a draw here. The idea is the following. I'm taking some point in the space, and I would like to know which image is going to be rendered in this plane, in this image plane. What do I do? Exactly what I said before. I'm taking I'm taking the ray between the camera center and a pixel. I'm shooting this ray. I'm sampling point on this ray, X, Y, Z, and I'm taking the direction into account, theta and phi, put it into the MLP and getting the color and the density, like here, like what you see here. For example, here I'm going to have a yellow color, and here I'm going to have the orange color, and here, I don't know what I'm going to have. But here, for example, the density is going to be very low, and here, because I have an object, the density is going to be very high. Okay, that's clear?
What I don't think is before we shoot array and see all the ways it reflects and what's the original light source that reflects that gives radiance to what we're seeing. In this case, we're just going straight. I don't understand where the light is coming from.
You're trying to understand how this is done in a classical manner, right? That's what we're trying to understand.
So this is all what the network takes care of?
Exactly, yes. Yeah. Okay. So, but it's very important to understand the idea here that every time you want to know what is the value in a certain pixel like this, you take a ray from the origin of the camera to the pixel, and then you have the viewing direction theta and phi, and then you sample points. You take this 5-dimensional vector, put it into the trained MLP, and get the color and the density, like what you see here. And then somehow you integrate the values of the color and the density to get the exact color that you have in this pixel. That's the idea. How the integration is done, we are going to cover it. But I just want to understand if everything is clear. Then you see how we choose? Okay. Essentially, you can choose anything, okay? Any point in the space. But in practice, if you are not in the cover of the dense cameras of the training, you'll get nothing. You'll get pushing. So you need to take something which is relatively, in this case of NeRF, you need to take something which is relatively in the distribution of the cameras. Yes.
Accent the shadow, the lights of somehow.
That's it, but it's implicit. You will see results and get some impression. It's not perfect. Then there are works that taking later many things into consideration. But here, the main point that they take the viewing direction into account, and this is very important when they take the viewing direction into account, because they somehow account for the BRDF of the materials, and somehow account for the light which come to the surface and how it is related to the normal of the surface. So taking into account the viewing direction is a great progress relatively to the other works.
Shape from shading, it's also can be done.
No, it's not related to shape from shading here. No.
I don't understand. I mean, you're speaking about specific X, Y, Z, so it's not the origin.
Again, I got you.
Each time,
Yeah.
X, Y, Z, it's a place.
On the ray.
It's a place on the array. So this is only the output illumination from this X, Y, Z.
Yes,
So actually, in order to get the image, you should integrate all the X, Y, Z.
exactly. That's it. You got it. Exactly. That's the idea. That's the idea of volume rendering. It's different from surface rendering. The idea of volume rendering is to take samples of the ray to get some information, the color and the density, like what you see here, yellow and orange. The density here is going to be 0, the density here is going to be 0, and then you integrate, and this is the idea.
The integration is like not with the equal weights.
Okay, the integration is quite complicated. We are going to cover it. It will take us some time, but this is the claim for fame. The rendering equation that they invented for the volume rendering. It can be explained mathematically, not just hand waving. We're not going to do it. Okay. So just talk about it. So how the training is before the rendering equation, how the training is it's done. You take the set of images with the known camera poses, and the idea is to reconstruct all training views by volume rendering. What do I mean by that? Like what we saw before. Here I guess that I say that I know that this image is here. I know the color, I know the position. This is not a novel direction or a novel position. And what do? I do the following. I'm taking the array, shooting the array, and train the network such that the resulting color here will be the resulting current of the neural net. Just let me, that's what I want to say. Okay. The idea is the following. Okay. We do what you saw before with the sampling of the point, and the loss is going to be such that the color in the pixels of the ground truths, which I do have, is going to be as much as possible close to the color of the rendered images in the training, okay? So I take a certain position, shoot some rays, and ask for the neural net, that the prediction of the neural net will be as similar as possible to the ground truth. This is the idea the training is done.
Which position is selected?
That's a real issue, because if I take the entire set of images and all the pixel, it will take a lot of time. They sample somehow, I'm not sure about which scheme, but they take just subset of pixel for one image, just subset of pixels for another image. Yes.
And you, what XYZ you are putting, because if part of the XYZ giving zero on the same.
We'll go over the rendering equation and you will see, but in the same manner that I described before, in the training phase, you know the value of the pixel here. You take the XYZ, you put it into the network, and you backpropagate the network such that the resulting color here is going to be as similar as possible to the ground truth color. And how do you integrate the XYZ? We are going to discuss it now, okay?
XYZ is global coordinate. Okay.
Yes, it's global coordinate of the specific scene, yes.
And how we are setting up the center of the camera.
The center of the camera is known. The position of the camera is known. The orientation of the camera is known. Otherwise, it's problematic.
I mean, we're testing our.
Well, in test,
Yeah.
yes, as I said before, we know more or less, in the case of NeRF, the cameras more or less sitting on a hemisphere. Okay, we know the position of the camera and the location of the camera, and we take more or less in the same density, in similar distribution of the camera. Okay, because I know all the location, all the orientation, I can render a novel image using this. Okay. Okay, so this is the idea. Everything is done in the differentiable way with respect to the density and the color. And also, this is also the claim for term. It's not easy. However, it's much easier doing differentiability of the network in the volume rendering rather in the surface rendering. It's totally different difficulties. Okay. So just to give you some intuition about the importance of the viewing direction that they take into account. So this is view 1 and this is view 2. This is the color for this viewing direction. This is the color for this viewing direction. You can see here all the possibilities of direction. And you see this is the same point in the 3D space, but from the different 3D direction, you get very different color. Here and here you see it, and this is very, very important. They made a lot of progress using this idea of the viewing direction. And we understand why, because we have different materials, we have surfaces that have different normals, etc., etc. Okay, let's just would like to say that this work has two key properties. The first one is the integration over the ray. And the other one is the way they represent the scene by coordinate scene representation. What do I mean by that? The XYZ is the input to the MLP, and the output is some characterization of the scene. Okay, this is the. Let's take a few minute breaks. What's the time exactly? Because any question before we move on? Because we are going to cover the rendering equation, and I would like you to be very focused on it. So, any question? It's a bit delicate. So, okay. So,
Can you explain, like,
just remind me your name.
Yuval?
Yuval. Oh, another Yuval. Yuval. Okay.
So I was going to take all the possible angles. Oh,
In the training phase?
yes.
No.
So
I'm going to sample. to sample angles from. Okay, just let me try to understand, to explain something. When you have an image plane, and you have the camera position, the orientation of the camera position, and you know where is the pixel, and you know where is the pixel, you can have just one line, which is the ray between the origin of the camera and the pixel. And this is one sample that we are going to. You do not take the entire set of pixels, and therefore you do not take the entire set of viewing direction. You just subsample from an image a set of pixels. And then you take another image. Actually, in the batch, you mix between the different images and not just work on just the image. It's more stable. And then you take another image and take some sample of it, etc., etc. And this is the way you will not cover all possibilities. It's expensive. Okay.
Questions. So is the RGB sigma, is this a matrix or a vector?
RGB, it's a vector.
Oh, sorry, like do we have multiple R's for each point that we sample, or do we have?
For each point X, Y, Z, I have one RGB. For each vector X, Y, Z, I have a vector RGB.
Okay.
Okay. Okay. The idea is that after training, the weights of the multi-layer perceptron, which consists of 9 layers, etc., etc. The scene is going to be encoding in the weights of a neural net. And then, as we said before, the input to the neural net is X, Y, Z, the viewing direction, and the output is going to be RGB and the density. Okay. And it looks like this, by the way. Let me explain. This is the input. This is the MLP. The viewing direction is not taken into account in order to predict the density, is only taken into account in order to predict the color, like what you see here. Okay. And actually, you can. This is theta and phi. For example, if this is the viewing direction, this is theta, this angle is theta, and this angle is phi. And also you can say that the viewing direction is the this vector on the hemisphere. You can just encode it like this. It doesn't matter so much, just to explain it. Okay. So now let's say, before we are going to cover the rendering equation, let's say that I shoot a ray, okay, and this is the density, which means that here I not have material, and here I have some material, and this is the color that I just predict. So it's important to understand that when I shoot a ray, I would like to know where is the first time that the ray touch the object. Why? Because that's what I will visualize. If the ray touch the object in many places, only the first place that I see is that what I'm going to see. Okay. So I would like to examine where is the first hit of the ray, and if so, I can guess that the first hit of the ray is here, and therefore this is the corresponding color that I'm going to predict. Okay. However, what happens if this is the density? I have nothing, something, nothing, something, nothing. What color should I predict here? Exactly. This one. Because I need the first hit of the ray. And I should neglect this one. All the rendering equation is all about how neglecting how to neglect the information which it's over the first shoot of the ray, and they are going to cover it now. Yes.
I don't understand so I don't understand what is the density, because
Okay.
it's 0 or 1. I mean,
It's not 0, and it's something between. It's a positive number.
what is the units of this?
No units. Just ignore units. Just a number, non-negative number. Between actually something which is close to 0. It can be also a very large number. And the idea of the density is to predict where do I have some material and where I do not have material. Okay, for example, if I have this, I don't know. If this is the object, I don't know, just like this, then the density is going to be something like this, this, and this. If I have some, just nothing here, okay? That's the idea.
Related to opacity.
It's related to opacity. Yes, it's related to opacity. When I have R, the opacity is going to be 0, and sigma is going to be very small, and vice versa. Yes, it's related to opacity. It's very related to opacity. Okay. So we need to combine the density and the visibility in order to get the required color. Okay. Now we are going to cover the volume rendering equation, and I'm not sure if it was explained in the paper in the beginning or after the paper was published. They tried to make it more intuitive. I'm not sure. I don't know, but I got this explanation and some of the slides from the people from Google, and I like the explanation. I'm going to explain it to you. So the scene is cloud of tiny colored particles. Okay, that's the idea that they cover. This is the volume that we want to scan. And if ray travel from the camera to the scene like this, a distance from here to here, and from here to here, I have a distance t. We call that the parameterization of a ray. It's O. O is the center of the camera. T is the parameter, and this is the direction. This is the parameterization of the ray. Then I would like to get the color at this place. I'll call it CT because it depends on the place on the ray. Okay, this is equivalent. O plus TD is equivalent to point XYZ on the ray. It's the same. This is also in R3. Okay. Okay. Now, what does it mean for a ray to hit the volume? So, actually, this is a probabilistic notion. Chance that ray hits the particle in a small interval around t is sigma t, which is the density, dt. Sigma is called volume density. So the chance that I'll hit the point at t is sigma t at very infinitesimal interval times dt. So if I'm here, I'll not touch the cloud of particles. Okay, if I'm here, I'll touch the cloud of particles. Okay, that's the idea of the density. Okay. Now, just recall what we said before. To determine if T is the first hit along the ray, we need to know something which is called T of T, the probability that the ray makes it through the volume up to T. What do I mean by that? The probability that we had no hits before T. This is called the transmittance. Okay? Okay? That's the idea. Okay, so we have two things. We have the density, sigma, and we have something which is called transmittance, okay, which is the probability that I didn't hit anything before I reached the position T. Now, if I'm using these two quantities, it means that the probability that I'm hitting the first the position T is going to be the multiplication between T of T and the probability that I hit T, which means that T of T times the density times dt, the transmittance times the density times dt. So far, so good. I'm not going to show you the derivation, but it's not very complicated, just a bit long. But it can be shown that given this density, I can calculate transmission T of T. This is the starting point. This is the point T. The transmission is exponent minus the interval of the density between T0 and T. believe me that it's okay. Let's move on because the later is going to be complicated. Okay, so now I can combine everything and say the following. P probability of the first hit T is going to be, as we saw before, transmission time density time small time interval. This is the transmission, this is the density. Okay, everything here is depends on the density, and we can move on. Okay. So now what is the expected color? The expected color is going to be the integral of the transmission times the density times the color at this point. Okay? Recall that T is also an integral by itself. Okay? Everything here is clear so far? How to integrate? Good. So I'm taking into account the first time I'm going to hit and integrate it by the color. Okay? Okay, how I'm going to solve the integral? I'm going to do some approximation, and that's what they do. This is the reason they take points on the ray, and then do some approximation. So we take how to approximate the interval. We take the ray and split it to small segments, starting by T1 till Tn plus 1, with some displacement between the next T and the previous T. Call it delta I. If something is not clear, just stop me. Okay. So now I'm going to approximate the integral using simple rule of numerical integration. This integral can be approximated due to this splitting by the integral from Ti to Ti plus 1 when I'm running from 1 to n. And I'm going to assume that in this small interval, Ci and sigma is going to be constant, okay? Roughly constant in every small interval. This is the reason I call it sigma in Ci. However, the transmittance is not going to be constant on this subinterval. And this is due to the reason that I want to know in any place where is the first hit and where is the block due to high density. If there is high density here inside the interval, I would like to take it into account. So this is a delicate issue that you are not going to replace it by some constant value. We are going to understand how to write this interval with some other way. Let's see how. Okay. So let's try to understand how to evaluate T. So let's take this is capital T and this is small t. Remember, T is the transmittance. Now we would like to evaluate T for any continuous value small t. So if small t is between Ti and Ti plus 1, I can take the integral which represents T and write it like Z. Okay, this is between 1 to Ti and this is between Ti to T. Okay? Okay, and we would like to evaluate capital T for continuous values of T inside the segment. Recall this, inside the segment. Therefore, this is very easy because we know the differences between Ti and Ti plus 1. This is very easy. I can move from here to here. No problem. So this means how much light is blocked by all previous segments up to here. Is this clear? Okay. Now I would like to understand what happens inside. Okay. And what happens inside can be modeled like this, and I can write it like this. Okay, this is straightforward. So how much light is blocked inside the current segment? Okay, taking everything together, I can write it as the following way. This is the integral, this is the approximation of the integral, and I'm going back from here, just back to here. Just to remind you, this is Ti, this is the quantity Ti. And I can write it like this. Ti sigma Ci with this expression that I just divided before. So in total, I have Ti. If I am going to open it and do the integral, etc., it can be shown that sigma, the density from outside, is going to be cancelled out, and that's what I have. Okay. let me try now to, maybe it's too fast, but at home I think you can do it and understand exactly what you're doing. Now, let's go to the most important part. So this is the integral, Ti times Ci, the points where I sample times something, which is 1 minus x minus density times delta I. This is called the opacity at segment I. Okay? This is called alpha I, this part. Okay? Alpha I is the opacity at segment I. Now, please look what happens here. This is Ti. Actually, Ti is the product of 1 minus the opacity. Where the opacity is going to be high, T is going to be 0, exactly. When the opacity, there is no transmission. When the opacity is going to be small, T is going to be not 0. It means that the transmission is possible. So all in all, it's very simple to understand, but the color of that ray is going to be Ti, which is related to opacity like this, come up to segment I. Look, this is up to segment I, which means I'm going to write it on the board if it's okay with you. So I'm going to have, maybe I have it in the next slide. Good, I have it here. Okay, so this is all the idea. Ti times alpha I are called the rendering weights, like you said before. I'm going to weight the color. It's not the same weights for each color. So here I measure using the opacity, Y minus the opacity, how much light is transmitted earlier along the ray, actually up to here. This is Ti. And here I measure how much light is contributed by the ray at this segment I. This is exactly the opacity, alpha I. So I have, up to here, I have what happens at the segment I, and here I'm calculating what happens at segment I. Okay? So 1 minus alpha 1 minus alpha 2, etc., until I'm reaching alpha I. Okay? Does it clear? Is it clear? Sorry. Okay. I hope so. If not, you can ask question or anything I can help you. Okay. So we saw that in this case, we'd like to get this color. And in this case, we'd like to get this color. And these are the rendering weights, Ti is time alpha I. So I have questions. Do you have any idea what are the rendering weights in this case? If I want what is Ti is time alpha I in this case? Any idea? If I'm going to get this color. These are going to be the weights. Very low here, high here, and again low here. Okay? Because here the transmission is blocked and I'm going to get 0. Okay? And here I don't have any material, so I'm going to get 0. And also here, it's going to be like the weights are going to be like this and nothing, because the transmission is blocked here, and I'm going to get 0 here. And this is the way I'm integrating the right color, which is the orange color and not other colors. Clear, more or less? Clear?
I'm supposed to have the sum of g's equal to 1.
The sum of these?
Yeah.
No, it's integration. You have to take into account the delta i's, and that if the delta i's are in right scale, it's going to be okay. You don't have that. Actually, they do something. When they start the pre-processing, they take the entire scene and somehow put it in a sphere with some dimension, bounded dimension, and they do something like what you said, but it's bounded in some dimension, but they put it in a sphere, they do something like this. But the integration is due to the delta I. Okay. Just let's try to understand how the sampling of the point is going to be done. So we sample on the ray. If we have some sparse uniform sampling, what's the problem? The problem is here, for example. okay? But here I have to sample more, and I miss it, okay? This is a problem. If I'm taking dense uniform in sampling like this, I'm doing too much. Here it's not enough maybe, and it's also inefficient. So what's in general when you have what you do in such cases? What?
Cross-validation.
You do coarse and fine. Like in many cases you do some coarse and some fine. So you have two networks actually. One is do uniform sampling at some equal space, and the other one is do non-uniform sampling due to the value of the sigma. Okay, where sigma is larger, then I'm going to get more samples. Okay, and we train them together. This is the loss. This is the true color. This is the predicted color of the coarse neural net. This is the color, and this is the predicted color of the final. Okay, and we train them together. Okay.
The way each one is same.
That's what I understand, but maybe I'm wrong. I don't know, but I think so. Yes. Yes. So let's see some results. And so this is after training the network with many images from very different viewpoints and having the scene implicitly in the network and the color implicitly in the network, the density, etc., etc. This is the ground truth. This is the prediction of NeRF. Here they show what happens if they do not take into account the viewing direction. As you see, it's worse because you don't have the effects of the lights like what you see here. And here we have something which I'm going to cover now. What happens if you don't make the trick, which is called positional encoding? Did you hear about positional encoding in the course? Yes, you heard about it. In which class? What? Interforming. Okay, that's good. So that's good. So what happens if you do not employ positional encoding? This is related to the lecture that we saw last time, that in neural nets, the components that are slow to convert are the high frequency components. And if you do not employ positional encoding, you lose the high frequency component in the conversion, like what you see here. Okay. So let's speak about positional encoding. I had this figure last time. We spoke about the spectral bias of the neural net. And we want to train a neural net to learn high frequency and low frequency. It first learns the low frequency, and only after many iterations, they get the high frequency. This is called the spectral bias of the full connected network. And here's the same issue, how to get MLP converts faster on high frequency target function. What do I mean by that? Okay, how to get this, so how to get this result and not this result. Okay? So let me try to understand it, to explain it. So the idea is the following. The input to the network is XYZ. And we are going to change the input to the network to something which is higher dimension in order to overcome the problem of non-converging high frequency. This was suggested by Tanchik et al. See what happens if you want to reconstruct an image. What happens if you do it without the trick that we're going to discuss? This is without the trick, and this is with the trick. This is with this positional encoding. Okay. Many applications. So it's very important. It makes a lot of good things to this. So let's move down to images and not to 3D, just to explain it to you. So in the case of implicit image representation, you take an image, you take some pixel of the image, you train the network, you put XY to the network in the input, you want to inference the RGB of the image. Okay? So That's what happens if I'm taking an MLP without doing any positional encoding. This is the supervision image, and this is the output. The network could not recover the high frequencies. Is it clear so far?
Is your reading from a model, like from shooting racing to?
No, I just said, I'm going now to move to a simple example.
But the MLP, how does it generate images?
Okay, good question. You're awake and it's good. Okay, so you take the supervision image, you sample points in the supervision image, X, Y, and RGB. You take this neural net, you train the net to get X, Y, and the output RGB, and then you are trying to take a point that you didn't sample in the training and to predict it. That's a good question. Okay, wasn't clear now. Okay, so that they take just one coordinate, X. This is X, I don't know, between 0 and 1, I don't know. Now I'm going to take this X, and instead of X, I'm going to put many coordinates instead of X. In a minute, we'll see which coordinate we're going to put. Okay? So now instead of X, I'm going to put sinus of some frequency times X. This is the different frequency. There are 5 frequencies here. So for each X, I'm going to get another set of values. Let me show it again. This is the standard input. And this is every X, I'm going to get very different values, like what you see here, which comes from science. Okay, and this is going to, I'm going to have a very large input, more than I had before, because I'm going to have high frequency, high dimension, like what you see here. Okay, and what is exactly this? Okay, so this is with this positional encoding, and this is without positional encoding. Okay, you see the differences. Same number of iterations, and you get what you wanted to get.
So positional encoding is the trick of using the sign.
In a minute, I'm going to explain how exactly. Okay, this is the trick. It's called also Fourier, a random feature Fourier component. It's not the first time it was used by Tanchik et al. It was used also by other people with some different strategy. Okay.
So it's a Taylor extension to some order out.
No Taylor extension, no. Let me try to explain it to you. Okay. No. You take each coordinate and you take a bunch of frequencies. What do I mean by a bunch of frequencies? You get you take X and instead of X, you are going to give input to the neural net, sinus X, like what you see here, or sinus pi X, sorry, sinus 2 pi X, sinus 4 pi X, up to some sinus, I don't know, dx, okay? So instead of just X, you are going to have D values. Everyone is coming from another frequency, okay? And you do the same thing with the cosine, okay? Like what you see here.
Why is it exactly like orders of 2?
Yes, it's order of 2. It doesn't have to be order of 2. This is the way they did it. You can also use another frequency. Just
infinite sequence of neuron frequencies.
Not infinite, but many frequencies. Yeah. Okay. And if instead of X, you are going to put this, and instead of Y, you are going to put this. It's a huge high dimensional input. Okay. Instead of Z, you are going to put, and also instead of the direction, you are going to use positional encoding. Okay? I'm going to explain. Okay. And you ask about the motivation, that's what I'm going to explain. Okay. The idea is the following. there are several ways to explain. The idea is the following. The problem with the convergence is the problem with the convergence of high frequency components. And this positional encoding take components which are high frequency, and using the positional encoding, they are no more high frequency. That's what I'm going to explain intuitively and then maybe more forward things. So let's say that this is the image that I want to learn. Okay, this is my target image that I want to take pixels and predict the color of the pixel. And in the training phase, okay, I take first this point, which I call A, which is white. And let's say that the coordinate of this point is 0.26 and 0.5. And the target value is what? Nearby, very nearby, I'm taking another point, which is red. Okay? And the coordinate here is 0.38 and 0.5. And the target value is going to be red. Okay. Now the neural net sees these two inputs. For the neural net, they're roughly the same, up to some noise, etc., etc. But the target is very different. So what the neural net does in such cases, some averaging, okay. But in another perspective, this is actually high frequency. Why it's high frequency? Because I almost have the same value of the independent variable, which is this, but very different value for the output. This is very different from this, but these are very similar. I cannot differentiate with them. This is exactly the definition of high frequency mode. Okay. So what do the positional encoding? Move, for example, here just very few frequencies, move from this input to this input, and from this input to this input. This allows the network to differentiate between this input and this input to get different values. And somehow you can understand that these are no more high frequency values. Therefore, they converge very, very well. This is important to this. And if we want it theoretically, it can be shown. It was shown, it's not very complicated to show. But if you look at the iteration matrix of the process of a gradient descent of the neural net, using positional encoding, the entire set of the frequency component are going to have the same eigenvalue, and therefore they're going to converge at the same time. This is theoretical. This is on show. This is related to what I spoke last time about the neural tangent kernel, etc., etc. This is the idea of the positional encoding. Okay, any question? Yes.
Isn't it actually like making all the image as high frequency?
No.
Because you move just a very short distance and the input.
Okay, let me try to.
Changes a lot.
No. Let me try to. So if this small, so this is the frequency. Okay, and this is the eigenvalue of the iteration matrix. Let's say, I don't know, M iteration matrix. This is the eigenvalue of the iteration matrix that correspond to this frequency. Why I'm speaking about the eigenvalue? Because it can be shown that the time that it takes us to converge is inversely proportional to the eigenvalue. So if this Fi and this is lambda I, okay, and the lambda I, the eigenvalue is very small, it will take you a lot of time to converge. If it's large, it will take you less time to converge. So if I'm going from here to here, from smooth to high, before positional encoding, it looks like this. And since the convergence time is 1 over lambda I, proportionally, this is going to be converged faster than this, because this is very small. What happens with positional encoding? Everything is going to be like this.
Exactly, but you deprive the network of the knowledge that the X and Y, in this case A and B, are very closely together. You deprive the network from this knowledge. So effectively, it has to like learn very high frequency of the input.
I'm looking it from some other direction. To me, everything is going to be equal, like what you see here. And this is the reason you can think about it. Everything is going to be smooth or everything is going to be high, but this is the idea of, okay, but actually it can be proven theoretically. We did it in our group, and it's a very nice idea, the idea of positional encoding. It helps a lot.
But you start having a lot more inputs though, right?
Yes.
So instead of 2 inputs.
So the first layer is going to be higher than the higher dimension that you had before, and then you. Yes. So let's see some results. Here is the result of NeRF, and here is the result for other approaches. Seems nice. This is synthetic results. Today the works will work better. Here I want to show that even with some tough materials, it works not bad from the perspective of rendering, but from the perspective of the surface reconstruction, it's not good. We'll speak about it in a minute. This is very famous data set. All of these are novel view synthesis. So you have the encapsulated scene in the MLP, and then you take a new position and you capture. This is the NeRF rendering. Okay, this is novel view synthesis. This is, by the way, without positional encoding. This is no, it's okay. This is without positional encoding. It's not great, but it's better. For example, here you see the small leaves, and here you don't see. It's not perfect. Okay. Let me show the example. So just to summarize and to understand the drawbacks of NeRF and what comes after NeRF. So novel view synthesis by volume rendering, by reintegration. It encapsulates the scene inside the MLP. The viewing direction is taken into account. It's very important. Otherwise, the result would seem worse. And just a minute. Okay, some drawbacks, some future directions. It is trained per scene. It's not generalizable. Every scene you should take the network, run it 4 hours, and get the representation of the scene in the MLP for this scene. It's very limited by the dense cover of the scene of the cameras. If you don't have camera in some dense in some places, you get garbage. It works well with many surfaces, but it struggles to work with transparent or glossy surfaces. And I think the most important issue is that the surface geometry is not characterized well by the density. And I want to explain what I mean by that. So here, for example, there are 3 scenes that are taken into account. This is from the paper by, it's called Unisert. Okay. And what they show here that if you take threshold for sigma, like what you see here, there is no sigma that actually will give you the surface itself separated from the environment, the exact detail of the surface. No sigma will let you have like what you see here, the star with the bear, with Buddha. Nothing is very good. It means that the volume density is good for novel view synthesis, but it's bad for geometry. If I want to construct the surface itself, this is a bad idea. And this is one of the main drawbacks of NeRF and related work that do not explicitly somehow take into account the surface. Therefore, in the next lecture, Meirav is going to speak about neural surface rendering and how you can exactly reconstruct the surface itself, the geometry, and not just do very nice novel view synthesis without taking into account the geometry. Okay? It's and even I have 5 minutes to have questions.
You do something that requires like real-time rendering, you're still stuck with rastering, right?
Real-time rendering?
Like if you're doing a video game or something like this, you cannot do these things which take time for
Okay, so if the training is prepared and you just have to do inference, it will take nothing. But if you want to take into account the training, it's a problem. There are today faster way to do the training also. There are some applications that do it, but the inference is always very fast. It does not take a lot of time. Okay. Any other questions? So next time we will get
Frequencies, how many frequencies include? What is the intuition for the frequency? Why not use wavelengths?
wavelet. It's okay, but not for now. But how many frequencies? That is a good question. It's a matter of tuning. It's not. We don't have a thumb of rule to. Or of some to know how exactly how many frequencies people just try. Okay. That's it. You know, it's an empirical solution.
So you're taking like a too high frequency?
No, in general, you take frequencies from low to high, always. How many low to high? It's a question. Actually, it depends on the content of the image somehow.
Yeah, you can.
Sure. Yeah.
Oh, that's all.
Yeah. You're right. But it's robust. It's very good to use it in many cases. Okay. So good luck with the project and feel free to ask questions with respect to the project and other things. And after Lior, there are some other nice lectures that you're welcome to attend. Okay, thank you very much.
Thank you.